What's going on, everyone? Right now we're going to go over the distance formula in both 2D and 3D, and hopefully by the end of this you'll be able to see, hey, I know why the distance formula is the way that it is, and I know how to use it in both two-dimensional and three-dimensional coordinate planes. Let's jump right in. Alright, so it is really helpful to know where the distance formula comes from, because it can also really help you remember this on a test and also make it a lot easier to apply it correctly given the appropriate circumstance on a problem. So this is a little bit of an example of just what it exactly that we're looking for. So let's go ahead and let's say, hey, let's go ahead and say that I have a line segment EG. And what this is going to do is it's going to represent a bridge that's kind of all over this water, okay? And so we're given endpoints because we slapped it on top of a two-dimensional Cartesian coordinate plane. And I'm going to go ahead and say that, hey, E is going to have a value of 1030. And then G is going to have a value of 6020 because again, kind of what's given to us. And I also know that this is going to be a right triangle. All right, so we got a little right triangle in there. Good information. So now let's go through step by step to see how we can kind of build this formula up. So let's say we want to find the lengths of EF and FG. Well, let's think about this. What is the coordinate of F? Well, it's going to be 1020 because I moved from 10 over here, 20 up, and that's going to give me my coordinate there. So what is actually going to be the length of EF? Well, if you think about it, I've gone 30 units all the way up here, and I've gone 20 units all the way up here. So in between these two, in between 30 and 20, as you can see, we've gone up a distance of 10. So I know that this is going to be a distance of 10. Let me actually mark that in a different color to make it a little bit easier. I'll mark that as a distance of 10. And then from F to G, if we think about it moving laterally from left to right, I moved 10 in this direction, and then I moved another 60 in this direction. So I went from 10, and then I went from 60, giving me a total distance of 50 units. So that's going to be 50 right here on the G. So went ahead and did that. So let's use the Pythagorean theorem to find the length of EG. So again, this is a right triangle. So I know that a squared plus b squared equals c squared. And I know that's going to be length squared plus length squared is going to be equal to the hypotenuse squared, the longest side, the one that's opposite of the 90-degree angle. So in this case, I have 10 squared plus 50 squared, my two legs, and I have my hypotenuse squared, which is EG squared. Okay, your calculator, you do 10 squared plus 50 squared. What you're going to find is that you're going to get a total of 2600 is going to be equal to the hypotenuse squared. So how do I get rid of that? Well, I just take the root of each side. And what you'll do is you'll find that you'll get an approximate answer of 50.9901 ... And that's going to be equal to your hypotenuse, EG. And if I want to go ahead and just simplify this down to three significant figures, I'll put 51.0 is equal to EG. So this right here has a length of 51.0. Okay, so now that I've gone ahead and I've established what EG is, and now it's asking me to use Pythagorean theorem to write a formula for the length of EG, the hypotenuse there, connecting the points E, which I called x1 and y1, and G, x2 and y2. So again, remember that these had coordinates of 10, 30, then G had a coordinate of 60, 20. So again, what I really did was I took the distance in between them to find the length, and then I took the root of that. Okay, so what's important to realize is that what you ended up doing was, in order to find 10, I subtracted 30 from 20. I subtracted whatever my my y was up here from whatever my y was down here. In this case, 30 minus 20, which gave me a leftover of 10. And then same thing here. If I had 10 here, I had 60 over here. Well, I went from 60, I subtract 10. That's going to give me a distance of 50 in between these two. So if I was asked to use the Pythagorean theorem to write a generic formula for the length of EG, that's really going to be asking us, hey, if we were given that E is x1, y1, in which case I use 10 and 30, and my G is x2, y2, which is 60, 20, how can I write a generic formula? So what's important to remember is, how did I get to this right here? How did I get to 10 squared and then 50 squared is equal to EG squared? So all I did was I used the Pythagorean theorem, but how did I get to 10? Well, my 10 was really just the height of this, right? It was really the difference between 30, which was how far I went up here, and 20, how far I went up here, and 30 minus 20 gave us my 10. So all I did was I took the difference in my y coordinates. So I took y2 minus y1, and I squared it. And that is exactly what 10 squared is. It's the same exact thing, except all I did was I used 30 and 20. Instead, now I'm just using y2 and y1 just as a generic formula. Okay? And then what did I do? Well, I added to that this right here, 50. In this case, it was the difference in my x's, because I went 60 all the way over here to 10 all the way over here. 60 minus 10 gave me 50 as a difference. So I'll go ahead and write that as a kind of generic x2 minus x1 squared. And then what did I do at the very end once I kind of simplify that down? Well, since this side was squared, my hypotenuse, and that's what I'm looking for, I went ahead and I took the root of it. So that's why I'm going to write this right here, the root. And what that is going to do is that is going to give you your distance formula. And in a textbook, you'll see it kind of written more like this, that the distance between 2 points, x1, y1, and x2, y2, is going to be the difference in the x's squared plus the difference in the y's squared. And what's important to notice is that it does not really matter if you put y's on this side and x's on this side. See how this side is switched? It doesn't matter because you'll be adding them. And what also doesn't matter in this case is that I use y2 and y1, and in here I use y1 minus y2. That also doesn't matter because, again, you are going to be squaring that value. So no matter what, you're going to end up with the same positive value after you square it. Okay? So that's really what it comes down to, is that, hey, we just took the difference in the y's, squared it, and we added onto that the difference in the x's, squared that. Then we just took the root, and that gave us our distance, which in this case was 51 units, because that was the hypotenuse. Okay, so that's where this formula comes from. It's really just noticing that you're doing the difference in the x's and the difference in the y's. You're squaring those differences, adding them together, and then eventually taking the square root to give you a distance. It's no different than finding the Pythagorean theorem with just the extra step of realizing that, hey, on a Cartesian coordinate plane, I just need to take the difference to find that length and the y's, and the difference to find this length for the x. All right, so let's take a look at how we can apply this formula in a different context. So now I'm asking, what is the difference between 2 points in 3 dimensions? So just like when we were taking the midpoint in 3 dimensions, we had that extra step on top. It's the same exact thing here, where we just have an extra set of values to take the difference of and then square that. So when I am thinking of my distance in 3 dimensions, I need to take the square root of the difference in my x's plus the difference in my y's. And then that was in 2D. And now in 3D, all I have to do is take into consideration that extra coordinate on the z-axis. Okay, and that's how you find the dimension. Sorry, that's how you find the distance in 3 points. Sorry, in 3 dimensions. So let's say that this first point right here is going to be what? Let's say that we are going to call this 2, 4, and then 5. Let's say we're going to call x2, y2, z2. Let's say we'll call that 6, 6, and 10. Okay, let's just say that's given to us. So all we have to do is find the difference in between the x's, and then the y's, and then the z's, making sure that we're squaring each of those differences. In fact, I actually made a mistake here. We got to square all 3 of these. Sorry. And then once we put that into our calculator, we'll get out an actual answer. So in this case, I would have the square root. So we can see the formula here. So I'll take the square root of, let's see here, I'll have 6 minus 2 squared plus 6 minus 4 squared plus 10 minus 5 squared. So once you put that into your calculator, and again, you can also simplify this even further by hand. You can write this as 4 squared plus 2 squared plus 5 squared. In any case, you put that in your calculator, you'll get an answer that's around 6.7082 ... Again, it depends on what your teacher's asking. Typically in my class, we do 3 significant figures. So I would go ahead and I would write this as 6.71. And again, I'm not giving any units, so that's going to be fine. So again, it's the same approach as when we do it in 2 dimensions, except we just have to do a third one, which in this case involves our z-axis, so we just have to take that into consideration. Same exact approach. So now let's take a look at how we can apply this in a word problem and do this step by step to figure out what the right answer is. All right, so let's say that we have a storage box for some garden tools in the shape of a cuboid. Okay, we go ahead and call that O, C, D, R, F, B, A, Q because of all the different vertices. All right, it's going to be shown in the diagram here. And let's say that the vertex A, I can go ahead and find that right here, A is going to have a coordinate of 2, 3, 4. What that means, again, we moved in the x2, we moved in the y3, and we moved in the z4 to get that point, 2, 3, and 4. Now what we want to do is find the coordinates of vertices R, C, B, and Q. So again, what we have to do is we have to use A to our advantage because I know that this is going to be 2, 3, 4. So it means that I moved 2 units out here, 3 units over here, and then 4 units up. So if I wanted to find the coordinates of R, well, I moved in my X by 2 and then nothing else. So what R would end up being 2, 0, 0. Because again, I moved 2 in the X, didn't move any in Y, didn't move any in Z, I'm stuck right there. So what would I do for the coordinate of C? So C is going to be over here. So again, I did not move at all in the X. I did, however, move in the Y. But how much in the Y? Well, remember that these two are going to be linked together, right? They're going to kind of reach the same value for Y. And so if I move 2 here, then 3 here, then that means this over here has to move a unit of 3 in order for me to line up and make this an actual cuboid, to make it an actual box. So I didn't move any in X, I moved 3 in Y, and then I moved 0 in Z. So if I wanted to now find the coordinates of B, again, B is going to be right here. So I didn't move any in X, I moved over 3 in Y, and then I moved over how many in Z? Well, again, this has to be the same height as A in order to make this a cuboid, in order to make it a box. So again, no X movement. I had 3 in the Y, and then 4 in the Z. So I'd have 0 in the X, 3 in the Y, 4 in the Z. All right. And then if I wanted to do the point of Q, which is going to be right here. So again, I'm going to move over 2 in the X. I'm not moving anything in the Y, but I am going to move up in the Z to get right here. And what is that going to give me? Well, again, everything up here is going to have a Z coordinate of 4 in order to make that a nice, even top for my box. So again, I moved 2 in my X, none in my Y, and then I moved 4 in my Z. So that would give me my coordinate there. And part B is asking me, what is the maximum length of a garden tool that can fit inside the storage box? Well, what you got to figure out here is that the maximum length is going to have to go from one corner to the other. If you just kind of logically think about that, it would be much larger than any other orientation that you could put something in. So another way of thinking about this is not how can this fit, but exactly what is the length or what is the distance in between R and B in order to make this fit. So again, I'm looking for the distance from R all the way to B in 3 dimensions. So again, if my coordinate of R is going to be 2, 0, 0, and my coordinate of B is going to be 0, 3, 4, well, now all I have to do is use my midpoint formula in 3 dimensions, plug these values in, and I'll get out the correct answer. So I'm going to be taking the square root of the difference in my x's squared plus the difference in my y's squared plus the difference in my z's squared, just like that. So again, I just recognized that my R is here, and I found out that my coordinate was that. I found that my B is here, and my coordinate is that, and I just plugged it into my formula, knowing that this is going to give me the distance in 3 dimensions. And what you'll find is that this is going to give us an answer of, cut right there because I actually don't. So once you put it in your calculator and you give it to 3 significant figures, you'll find that the distance from R to B is going to be about 5.39. Again, we're not given specific units here, so that'll be just fine for our use case right now. Now, how about C? The height RQ of the storage box. So how high is this thing? So if I want to know how high it is from R to Q, and it should be noted that it actually doesn't matter if it asks for RQ or OF or CB or DA. It'll all give us the height. And again, what we're asking is, hey, what's the distance between this point down here on the base of this thing all the way to this point right here on the top? So again, I'm going to do the same exact thing. I'm just going to find my distance from R to Q. So I know that R has a coordinate of 2, 0, 0. And I know that Q has a coordinate of 2, 0, 4. I'm going to plug that right back into my equation. So the root, or I'm sorry, my formula. So I have the root of 2 minus 2 squared plus 0 minus 0 squared I don't know why that looks so ugly. Plus 0 minus 4 squared. And now you might already be able to tell that this actually made it pretty easy for us to solve, because 2 minus 2 is 0, so that's gone. 0 minus 0 is 0, that's gone. We have 0 minus 4, that's negative 4. And we're going to square negative 4. So again, I'll be left with negative 4 squared, and that's going to give me the root of 16, and that is going to give me a final answer of 4. So again, 4 units, whatever the unit of measurement happens to be, that is going to be the distance from the base to the height, and is going to give us the overall height of that box, which in this case is just 4. So part D is asking us, hey, what exactly is the angle between BR, which is going to be right here? We said that that has a length of about 5.39 when we approximate it, and then BQ, okay? Well, if you notice that if I'm taking this into consideration, and I know that the end of this point and then the end of this right here is going to be the height of it, well, let's actually draw that out as a triangle. So I know that this would have a value of 4, and then I know that this would have a value of 5.39, and I know that this is the theta that I'm looking for. So if I B right there, R right here, and Q right there, I want to know exactly what that angle is. So how exactly am I going to find this? Well, if you think about it, this is a 90-degree angle because, again, that is going to be where the surface meets the height of a box. It's going to be a perfect 90-degree angle, as you've seen on boxes before, or cuboids. Well, now I can kind of think, well, hey, this might look kind of familiar because I have a 90-degree angle. I have this right here. And so if you think about it, I am given the value of the opposite side of my triangle as well as the hypotenuse. So if you remember the old SOHCAHTOA, which one of those is actually going to be useful here? Well, again, I have the opposite side as well as the hypotenuse. That's going to be sine. So the sine of theta is going to be equal to opposite 4 all over 5.39. Now, how exactly do I go about this? Well, again, if I'm looking for the sine of a theta, I need to do the inverse operation in order to isolate theta, which in this case would be the inverse sine. So now I know that theta is going to be equal to the inverse sine of 4 all over 5.39. And it's important to note that I'm using the approximated value, 5.39. Oftentimes that's okay, but sometimes you actually really want to make sure you're using the exact value, which in our case was going to be 2 root 29. That is what is going to give us this 5.39 over here, as we went over before. And if we put this into our calculator, we'll find that if we round to 3 significant figures, theta is going to be about 21.8 degrees. So again, that's combining a lot of what we have gone over so far, and also something new, perhaps something part of review, is that, hey, we have been going in 3 dimensions here, x, y, and z. We have been finding out the different coordinates of different vertices on this box. We've been using the distance formula to figure out what the value is of the longest gardening tool that can fit inside this box. And then using the value of the height as well as the diagonal that goes across for the longest shape, we extracted out of that a right triangle, and then from there we just used our simple SOHCAHTOA properties and found that the angle that was going to be from between BR and BQ to be 21.8 degrees. So again, these can be simple when they're isolated by themselves, but a lot of times these mathematical concepts that are gone over throughout the course of a year really can be stacked on top of each other. So it's always really important to remember what you've gone over and keep diligent notes. So that way you can keep referring back to them and be able to use those properties and ideas to solve for the correct answer no matter where you are in the term. All right, so again, I hope that helps. I hope that you now see that doing the distance formula in 3 dimensions is just as easy as it is in 2. And again, the basis of this is the Pythagorean theorem on a Cartesian coordinate plane. And if we throw in that 3rd dimension z, not a whole lot changes. We just take in another 2 numbers to subtract and then square and take the root of after we add it to the rest. Okay, so I hope that helps. It is a little bit more complicated. Make sure you practice, and I'll see you all in the next video.